Today we're going to talk about power series. As a warm-up, let's find the interval of convergence and the function of x that's represented by these geometric series. So if we take a look at number 1, sum of n equals 1 to infinity of 3 to the n times x to the n, that's the same thing as the sum as n equals 1 to infinity of 3x all to the nth power. And so we have a function basically that's looking something like this. So we have f of x equals 3x plus 9x squared plus 27x cubed, and so on. So if we take a look at that and we try to find the interval of convergence for that, the interval of convergence is going to be somewhere between -1 and 1 for a geometric series, obviously, because we have something to the nth power. So for a geometric series, it has to be between -1 and 1. So we know that x converges between 1/3 and -1/3. We actually will have to do a little bit more testing later on, and I'll try to remember to come back and see if any of the endpoints works. But hopefully I remember to do that at the end of the video. In this problem, this is also a geometric series. So we would have a function that looks something like this. So if we're starting at 0, we have 3 plus, looks like 3 times x minus 1 over 2 plus 3 times x minus 1 over 2 squared, and so on. So that one, it's pretty straightforward. You could rearrange it so it ends up being 3/4 times x minus 1 squared, and then the next term would be 3/8 times x minus 1 cubed. You could rearrange that as well. But this is our value of r, so we need to do -1 is less than x minus 1 over 2, which is less than 1. So when we solve that, we get -1 less than x less than 3. I skipped a couple steps, but that would be how you solve that. And once again, I'll try to come back to that and test our endpoints as we move along and see what happens. So the definition of a power series: if x is a variable, then any infinite series that has this form, so the sum from n equals 0 or n equals 1 or whatever to infinity of a sub n x to the n, which is equal to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub n x to the n, and then going on. If it's infinite, it'll go on forever. That is called a power series, and it's centered at x equals 0. Now we could center it at some other value. For example, we'll center it at c in this particular case. So we have the sum from n equals 0 to infinity of a sub n times x minus c to the n. So I'm basically going to rewrite this, except anywhere there was an x, I'm going to have an x minus c. So it's a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub n times x minus c to the n, and so on and so forth. That's called a power series that's centered at c. So if we want to center the power series at some other value of x other than 0, that would be how we do it. And this would be a function of x here, because if you multiplied it all out, that looks like a polynomial. So that's what a power series is. So once again, if I look back at this second example that I had, I could have rewritten this so that it's a little bit easier to see that it's a polynomial of that form. So I could have 3 plus 3 times x minus 1 over 2 plus 3 over 4 times x minus 1 squared plus 3 over 8 times x minus 1 cubed, and so on. So it's pretty clear that I have some sort of center, like here my center is at x equals 1. So in this case my c would be 1. And then moving along, I have some constant in the front of every term, and the center is being squared, then cubed, then to the 4th power, and so on. Notice that the convergence interval of that problem is centered at 1, and notice that the first problem, the convergence interval, was centered at 0. So if we're looking at the couple more examples here, so if we take a look at this example, if I try to write this out, I get x plus x squared over 8 plus x cubed over 27 plus x to the 4th over 81, and so on. And this problem in number 2, I have, notice it starts at 1, so I have x minus 1 plus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on. So these are examples of power series where I am writing these. Basically, it's a function where my polynomial x values are getting squared, cubed, fourthed, and so on as we go along. So these are just polynomials that continue to grow in power. So a power series of x can be viewed as a function of x, and that's kind of what I was talking about. Be careful, that doesn't mean x factorial in this case. So we have f of x is the sum of n equals 0 to infinity of a sub n times x minus c to the n. So I can take this power series and I can view it as a function that goes on forever. Let's talk about the convergence of power series. Convergence of power series basically follows the same principles as the convergence of a geometric series, because if you notice, we have some term that's multiplied by some value of x to the nth power. So if I'm taking a look at this particular thing, my r is on the inside. So it's r to the n here, basically. So I have 3 different options depending on what happens with x, and we'll talk about it throughout this worksheet. First, the series converges only at c, so it only converges at the center. Secondly, there is a real number that's greater than 0, such that the series converges absolutely for x minus c is less than that number, and it diverges for the absolute value of x minus c is greater than that number. And then the series converges absolutely for all x. Those are our 3 options. Now, if I'm looking at option 2, whenever I have a situation where option 2 exists, my endpoints must be checked separately. And that's why I'm going to go back to the beginning of the worksheet if I remember correctly, or if I remember to do that later on. Example, create a power series from the function f of x equals 1 over 1 minus x. So if I recall, this looks a whole lot like a over 1 minus r. So that means my a is 1 and my r is x. So that means this looks a lot like the sum from n equals 0 to infinity of 1 times x to the n. So that's going to be 1 plus x squared plus x cubed plus x to the 4th plus x to the n. So since this is a geometric series, I can check for the interval of convergence. The interval of convergence is between -1 and 1. So if it's asking for the radius of convergence, the radius of convergence is going to be, if I look at a number line, this converges, centered at 0, between -1 and 1. So if I'm looking at the radius of convergence, if I thought about this as like a diameter of convergence, the diameter would be 2. The radius is from the center to an end, so the radius of convergence is 1. So if I'm looking at my interval of convergence, that's from -1 to 1. I'm looking at the radius of convergence, that's equal to 1. So if that helps you to look at it geometrically, that is what's going on there. And once again, we will check the endpoints of this in a minute, after I show you something where I do check the endpoints in problem 3. So find the radius of convergence of the sum of n equals 0 to infinity of n factorial times x to the n. So first thing I'm going to do is, if I look at this problem, a lot of times when we test for radius of convergence or interval of convergence, a lot of times what we will do is we will use a ratio test, basically, and kind of see what happens in the ratio test. See if it even converges really anywhere other than x equals c. So if I take the limit as n goes to infinity of n plus 1 factorial times x to the n over n factorial, I'm sorry, x to the n plus 1, so n factorial x to the n. What I will do is notice that n plus 1 factorial over n is the same thing as n. Sorry, n plus 1 factorial over n factorial is the same thing as n. And n plus 1. Doggone, Jason. It's the same thing as n plus 1. And then if I do x to the n plus 1 divided by x to the n, I end up with just x in the numerator. And so I have n plus 1 times the absolute value of x. Remember, this is inside of an absolute value. And as I go to infinity for n, then this becomes infinity. So this diverges for all values except for at x equals 0. So if you notice that at x equals 0, it's 0 times some number, and that's going to be 0. So it converges only at x equals 0. And if you notice, when I have x to the x equals 0 here, that'd be 0 times stuff. So it converges only at x equals 0, and the radius of convergence is 0. Problem 3. Find the interval of convergence of the sum of n equals 1 to infinity of x to the n over n squared. So the first thing I'm going to do is I will do the ratio test, because the ratio test works a whole lot for this thing. So I'm going to have x to the n plus 1 over n plus 1 squared divided by the those terms just to the n, so I'm going to multiply it by the reciprocal. So it becomes n squared over x to the n. So if I look at this, x to the n plus 1 over x to the n is just x in the numerator. I should write a limit. Limit as n goes to infinity. So that's an x in the numerator. And in the denominator, I basically end up with, well, I have this n squared over n plus 1 squared. And if I take n goes to infinity, I know I could use L'Hopital's rule, or I could use pre-calculus rules. And this goes to 1. So as n goes to infinity, this is just absolute value of x. So where does that converge? If I take n going to infinity, that will converge as long as as long as x is between -1 and 1. Because this is basically what I have right here. This is basically a geometric series with x to the n. So that will work as long as x is between -1 and 1. So now I'm going to check the endpoints. So when I check endpoints, what I'm going to essentially do is I'm going to see if either of those endpoints works, or if one of them works and one of them doesn't, or vice versa. So if I take a look at x equals 1, so if I take a look at x equals 1, that means the sum of n equals 1 to infinity. I'm just going to take 1 and substitute it in. So I get 1 over n squared. That is true all the time. That converges by the p-series. So now what if I take x equals -1? So I have the sum of n equals 1 to infinity of -1 to the n over n squared. That converges not only by the p-series, but by the alternating series test that would also converge. And so therefore, both x equals 1 and x equals -1 work. So my interval of convergence is -1 to 1 with brackets, and my radius of convergence is 1. Problem 4, find the interval of convergence of this series. So notice it's an alternating series. First thing I'm going to do is find the interval of convergence not taking into account the endpoints. So limit as n goes to infinity of x plus 1 to the n plus 1 over 2 to the n plus 1. And then I'm going to multiply by the reciprocal. So that's going to be 2 to the n in the numerator and x plus 1 to the n in the denominator. Notice I'm not taking into account the alternating part because this is the ratio test and I'm doing absolute value of this. So when I take this, I get the limit as n approaches infinity of x plus 1 in the numerator and 2 in the denominator. So if I look at this, I don't have n's anymore. And so basically what I have to do is when x plus 1 over 2 is between -1 and 1, then that ends up working out. So x plus 1 over 2 is between -1 and 1. So I multiply by 2 and I subtract 1. So I get -3 less than x less than 1 is my interval of convergence. Now I'm going to check for endpoints here. So if I look at this, when x equals -3, I have -3 plus 1 is -2 up here. So I have -1 to the n times -2 to the n over 2 to the n. And this is a little bit confusing, but notice that when you look at the numerator, they're both going to be positive or they're both going to be negative at the exact same time, because when n is odd, then both of the numerator parts are odd and you multiply them together, it's an even. If n is even, then they both become even anyway. So this is basically the same thing as 2 to the n over 2 to the n, which is the same thing as the sum of 1 from n equals 1 to infinity, and that's going to diverge. If I have x equals 1, then what I have is -1, the sum from n equals 1 to infinity of -1 to the n times 2 to the n over 2 to the n, and that is, these end up canceling. I get the sum from n equals 1 to infinity of -1 to the n. That diverges by the nth term test because the nth term does not go to 0. So that means that the endpoints both diverge, and -3 to 1 is my interval of convergence, and my radius of convergence is 2. So let's go back and talk about the first two problems that we had. So if I look at this, if I check endpoints, so if I check 1/3 and -1/3 in the first problem, notice if I plug in 1/3 or -1/3, I end up with the sum of n equals 1 to infinity of 1 to the n, which diverges, or the sum of -1 to the n, which also diverges. We talked about both of those cases in the last problem. If I'm looking at the second problem here, if I check 3, I get 3 minus 1, which is 2 over 2, so I get 3, and that won't work. If I check the second part and I plug in -1, I get 3 times -1 to the n, which once again won't work because we already checked both of those. But now let's check problem 1 for the interval of convergence of this power series 1 over 1 minus x. If I check 1 and -1, I end up with the exact same things that I did in the last couple problems. So I end up with the sum of 1 and the sum of -1 to the n, which both diverge, and so therefore my interval of convergence does not include the endpoints. All right, now let's talk about differentiation and integration of a power series. By the way, one other thing that you might want to note is that it is true sometimes that the one endpoint converges and one endpoint diverges. So we have not talked about any of those cases, but it is possible, and it's also possible that we might end up with a case on this page. 1a, write out the first 5 terms of this power series. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. So these are the first 5 terms, and then obviously it keeps on going forever. Part B, take the derivative of this series. So in order to take the derivative of this, what's one thing that's true about power series is if you take the derivative of each of the individual terms, that is going to be the same thing as taking the derivative of the summation. So I will take the derivative of each of these terms. The derivative of 1 is 0. The derivative of x is 1. So f prime of x is going to be 0 plus 1 plus derivative of x squared over 2 factorial is going to be 2x over 2 factorial, which is just x. If I take the derivative of x cubed, that's 3x squared, and then that's divided by 3 factorial. So if I take a look at that, that's 3x squared over 3 factorial. Remember, 3 factorial is 3 times 2 times 1. So the 3's cancel, and I'll end up with x squared over 2, or x squared over 2 factorial. And now if I take a look at the term x to the 4th, I get 4x cubed over 4 factorial, which is 4 times 3 times 2 times 1. The 4's will cancel. I'll end up with x cubed over 3 times 2 times 1, which is 3 factorial. And let's just take the x to the 5th term. So that'd be 5x to the 4th when I take the derivative over 5 factorial, which is 5 times 4 times 3 times 2 times 1. Those cancel. I end up with x to the 4th over 4 factorial. So what I appear to be noticing is that my derivative is exactly the same as my original function. And there is a function that is true for, that we already know the derivative of the function is equal to the original function. And I'm going to point out to you that that function is e to the x. So if I take the derivative of e to the x, I get e to the x. If you turn it to the back and you want to write this down, it might be interesting for you. One thing that you should know if you don't is that 0 factorial equals 1. Also, what I did was I'm now taking some function of x and I'm making it equal to 2x to the n over n factorial. So I'm basically replacing x with 2x in the previous problem. So I just wrote all this stuff out. In the interest of time, I wrote it out a little bit earlier, so I'm not writing it all down. F prime of x, I'm just taking the derivative, and I'm taking the derivative using the chain rule instead of doing 4x squared and then just writing it as 8x or 8x cubed and writing it as 24x squared. So I'm using the chain rule instead. So I'm doing everything on the green in the original problem. The part that's underlined by blue, the 1, that just goes to 0. So if I take a look at this, I factor out a 2 and I get 1 plus 2x plus this part got factored out, and then 3 and 3 factorial the 3 will cancel out and I end up with 2 factorial there. So I have 2x squared over 2 factorial. Notice the 2 got factored out, and then the 4 and 4 factorial will cancel, and I'll end up with 3 factorial. So I have 2x cubed over 3 factorial, and so on. And so basically what I end up with is the original function, except I have a 2 on the outside. That makes sense because since I know that f of x, if this function was just x to the n, would be e to the x, that means that this function should be e to the 2x, and I know that the derivative of e to the 2x is 2 e to the 2x. So notice that this stays exactly the same as the original function was, and then I have a 2 on the outside. I don't know what in the world is occurring right now. Okay, consider the function f of x equals sum of n equals 1 to infinity of x to the n over n. So notice it's not n factorial, it's just n. Write out the first 5 terms of the power series. So f of x equals x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus x to the 5th over 5. Now it's asking us for the integral and the derivative. So the first thing I'm going to do is integrate this. So the integral of f of x dx, that's going to be x squared over 2 plus x to the 3rd over 6 plus x to the 4th over 12 plus x to the 5th over 20 plus x to the 6th over 30. And so if I want to write that as a sum, that'd be the sum of n equals 1 to infinity. And it looks like I'm having x to the n plus 1 in the numerator. So I'm going to start with x squared. And then the denominator appears to be n times n plus 1. So notice this is 1 times 2, this is 2 times 3, this is 3 times 4, this is 4 times 5, this is 5 times 6, which makes sense because all of these terms here just got multiplied by a number bigger than them. So that is my sum. Now if I want to determine the interval of convergence, I do the limit as n goes to infinity of I'm going to do the ratio test. So I have x to the n plus 2 over n plus 1 times n plus 2, and then I'll multiply by the reciprocal. So I have n times n plus 1 over x to the n plus 1. So I get the limit as n approaches infinity of x. And then I have the n plus 1's cancel, and I have n over n plus 2. And I know that as n goes to infinity, this just ends up being the absolute value of x. So my interval of convergence is -1 less than x less than 1. I have to check the endpoints. So at x equals -1, I have -1 to the n plus 1 over n times n plus 1, which is the same thing as n squared plus n. So that's the sum as n equals 1 to infinity. If I look at that, that converges not just by the alternating series test, but by direct comparison with a p-series or a limit comparison with a p-series. So at -1, that works. So I'm going to make that a less than or equal to. And then if x equals 1, I end up with 1 to the n plus 1, which is just going to be 1 over n squared plus n. That also converges by comparison to the p-series. So my radius of convergence is 1, and my interval of convergence is -1 to 1. Both of them are inclusive. Okay, so if I take a look at f of x is the sum n equals 1 to infinity of x to the n over n. So I will do the ratio test, limit as n approaches infinity of x to the n plus 2 over n times, or n plus 1, sorry, times n over x to the n plus 1 Again, multiplying by the reciprocal. So this ends up being the limit as n approaches infinity of n over n plus 1 times x, which is once again the absolute value of x. So -1 less than x less than 1. If I check the endpoints at x equals -1, I have the sum of n equals 1 to infinity of -1 to the n over n. And I know that converges by the alternating series test. So I need to put an inclusive sign there. And then at x equals 1, I have the sum of n equals 1 to infinity of 1 over n, which diverges because it is the harmonic series. And I know that by the p-series test that diverges. So therefore, the ratio test and all the subsequent testing of the endpoints give me -1 inclusive to 1 exclusive. So my radius is 1 and my interval of convergence is -1 with a bracket and 1 with a parentheses. So now if I take the derivative of the original function, f prime of x equals 1 plus x squared plus x cubed plus x to the fourth, and so on. This is the sum of n equals 1 to infinity of n minus 1. Sorry, no, that's a lie. Sum of n equals 1 to infinity of x to the n minus 1, which is the same thing as the sum of n equals 1 to infinity of x to the n plus 1. So that is something that we have actually already done. If we look back at this problem, we have already done this problem. It's the sum of n equals 0 to infinity of x to the n. It's the exact same thing. We can just write it in a bunch of different ways. So the sum of n equals 0 to infinity of x to the n. And if I'm looking at the interval of convergence there, I know that it is -1 to 1. I've already checked the endpoints previously, so I know my radius is 1, and my interval of convergence is -1 to 1, both with parentheses.